Okay, we're continuing with Chapter 8 in the trigonometry textbook. Right now we're learning about complex numbers. In this video, we're going to go through the last section of Chapter 8 on complex numbers, where we're going to learn how to find powers and roots of complex numbers. So we've learned how to add, subtract, multiply, and divide complex numbers. Now we're going to learn how to find powers and roots of them. And de Moivre's theorem is about finding powers. So, okay, this is really interesting because you can think about the main reason complex numbers were invented was for answering questions related to even roots of negative numbers. So being able to find even roots of negative numbers. So we know if we had the square root of negative 4, or the principal square root of negative 4, we know how to evaluate this, right? But what about something like the fourth root of negative 16? How do we think about what numbers, when you take them to the fourth power, do you get negative 16? Well, once we learn how to find roots of complex numbers, we'll be able to answer this question. Okay, now, but before we get into this section, what you can notice is that there's going to be some confusion here regarding radical symbols and how that's, this is going to be really confusing, and I'm actually going to make a whole separate video on talking about this. So remember the radical symbol, okay, the nth root, the nth, not root, any radical symbol, no matter what the n is, that's referring to the principal root of the radicand or the argument. So even if you have this, you're asking for the principal cube root of 8. A radical symbol, it's not just with square roots or even roots do you say principal. Any radical symbol means principal root. Okay, so just keep that in mind as we go through this section, and I'll elaborate further on where this confusion is going to come in with these radicals and roots of complex numbers as we go forward. Okay, but just it's important to note that when we're talking about roots of numbers, there's two perspectives. There's the principal root of a number, but then there's the more general just question of, okay, given a number like minus 16, or you could kind of look at that as minus 16 plus 0i, or, 2 minus 3i. You could look at any number in the complex plane, any number that exists in math, and you can ask a question of, okay, from a fifth root perspective, what you're asking is, what numbers, when you take them to the fifth power, do you get minus 16? That's going to be a fifth root of minus 16. Or what numbers, when you take them to the fourth power, do you get 2 minus 3i? Those are going to be fourth roots of 2 minus 3i. Okay? That's that general overarching question is different from having something inside of a radical symbol. Anytime you have a number inside of a radical symbol, you're never asking that general overarching question. You're asking for what the principal root of that number is, which is different than that general question of what are all of the roots. Now, but you might think, well, wait a minute. I feel like I've used radical symbols before in relation to that general overarching question. Well, the only time where there's a radical symbol involved with that general question of what are all of the roots is for the same reason why, if we're solving an equation like sine of theta is equal to root 2 over 2, we want to solve for theta. Well, we introduce the inverse sine, apply that to both sides to get the theta out, right? And now, in this situation here, the inverse sine function is only one value, right? But since we introduced the inverse sine function, we're going to go ahead and answer the general overarching question. What are all of the angles? Not just between 0 and 360, just across the board, that when you take their sine, you get root 2 over 2. And then we listed out all of those angles. There was an infinite number of angles. Well, we kind of do that same thing when it comes to radicals and equations. Like if you were solving the equation x cubed is equal to 8. Okay, well, to solve this, what we do is we put this principal cube root. We take the principal cube root of both sides. Okay, and now we're left with the principal cube root of 8, which we know is just any principal root of a number is going to be, by definition, one number. It's a function. Okay, but it's just like with the inverse trig functions, we're actually going to, since we introduced this, we're going to answer the big picture question of what are all of the numbers in mathematics or in the complex plane that when you cube them, you get 8. And the answer to this equation would be you'd list out all of those numbers, right? But you might be thinking, well, it doesn't matter anyway, because in general, there's only one number that when you cube it, you get 8. That's 2. So there's only one answer to the equation x cubed is equal to 8. In the same way that if you had x cubed is equal to minus 8, that's actually just going to be the principal cube root of minus 8. Well, what we're going to learn in this section is that, so as a consequence of inventing complex numbers, of inventing the entire complex plane, what happens is that, so there's a general rule that we're going to learn that if you take any complex number, so this includes, any number in the complex plane includes all real numbers, so this includes the number 8 as well, right? That's 8 plus 0i. Any complex number, and you ask the question, what are its cube roots? What are all of its cube roots? What are all of its fifth roots? So again, we're not talking about like a principal root. We're asking, what are all of the numbers, like 8 plus 0i? What are all of the numbers in the complex plane that when you cube that number, you're going to get 8 or 8 plus 0i? Then there's going to be n of those roots. So what are all of the cube roots of 8? There's going to be 3 of them. If you say, so what are all the nth roots of any complex number z? There's going to be n of those roots. So in actuality, if you're talking in complete general here, solving the equation x cubed is equal to 8, and in all of the complex plane, there's going to be 3 numbers that when you cube them, you're going to get 8. One of those is going to be 2 plus 0i. But then the other 2 are going to have an imaginary component. Okay? But again, though, even with that, I just want to point out that this is we're really not looking at this here like it's a principal cube root, in the same way that if we were solving an equation and we used inverse sine to isolate a theta, even though this is the inverse sine function, there's only one output here, just like there's only one output to a principal root. We're just not thinking about it that way just because we introduced it. We're still looking at the big picture. Okay, now, but what we want to do, though, is the mindset you want to have, and this does get kind of confusing, is that, so I've mentioned before that there's kind of 2 contexts that, in particular, non-mathematicians, they're just like engineers, etc., that do apply math. There's 2 contexts that we put ourselves into when we're talking about numbers in math. So there's, and you're aware of this, sometimes all you're talking about is the set of all real numbers. Even though, like, you can think about the real number line is within the complex plane. Right? We know this. The complex plane, the horizontal axis is like the real number line. Okay? This is the set of all real numbers. But there's still a kind of, in certain conversations, there's a context we have where we're thinking about all real numbers existing in their own world, kind of like from the perspective of before imaginary numbers were invented, that's how we were thinking about things. Okay, but then there's another context where we're actually thinking about all numbers that exist in mathematics. So we're thinking about the complex plane, and in that sense, we're thinking about a number like 8 here. We're thinking about that as a complex number, 8 plus 0i, right? And that's when we're thinking about the complex plane. But you'll hear they don't want you're not supposed to, even in the complex plane, you're not supposed to do this. Put like this as the set of all real numbers. No, this is the set of all complex numbers. Okay, so you just put real here and imaginary here. So you're not supposed to mix in this set of all real numbers in with this, even though that is like, it's kind of like you took the set of all real numbers and put them on the horizontal axis here, but you're not supposed to look at it that way. Okay, and so with those 2 contexts of how we kind of view and talk about numbers. What we want to do is, anytime there's a radical involved, except for this case where you introduce it to solve an equation. Other than that, anytime there's a radical involved, we want to be thinking in terms of this context here, just the set of all real numbers, with the one exception being what we learned about square roots of negative numbers. We're kind of thinking about a complex number here, right? Because it's like you take out a 4, you're bringing in the imaginary number. So except for that, except for this. And so in that sense, I really didn't want to write this here. Like a minus 16 inside of a fourth, a principal root with an even index other than 2. Well, I mean, no, we can put this. This is fine, but this means, no solution. In the same way that when we originally learned radicals in pre-algebra, if you had the square root of minus 4, that if you had any negative number inside of an even root, you said no solution. Right? We're not even going to. That's what I'm saying. We're not even going to think about imaginary numbers with radicals, except for the case of a square root and a negative number inside the root. It's just going to create confusion. You might be saying, well, what's the big deal? Why all of this confusion? Why all of this conversation about radicals? Maybe I guess we don't want to mix complex numbers with radicals because there's no such thing as a principal root of a complex number. But that can't be the case because, technically, like the number 8 is a complex number. This is 8 plus 0i. And it does have a principal cube root of 2. So maybe it's the case that only pure real numbers have principal roots. So in the complex plane, only numbers on the x-axis have principal roots. Well, we're going to learn in this section here. I think I'm going to split this up into 2 separate videos. So in the next video, we're going to learn that no, actually, any complex number in the entire complex plane. So it's going to have nth roots. The nth root of the complex number is going to have n separate roots. And one of those is going to be the principal root of that complex number. So actually, every number has a principal root. So you might be thinking, well, okay, well then what's the problem then? That's actually great news. We can do this. The principal nth root of z and just put whatever that principal root is. Perfect. Well, unfortunately, it gets kind of confusing because what we're going to see is, like, for example, we know that the principal cube root of 8, or of minus 8, is minus 2, but from the complex number standpoint, like once you get into more advanced courses on complex numbers, like complex analysis, which I'm going to do a playlist on, the principal cube root of minus 8 plus 0i, yes, while minus 2 plus 0i is one of the cube roots of minus 8 plus 0i, that's actually not the principal cube root of minus 8 plus 0i. And so that's where it gets really confusing. And so, but like, they are in complex analysis, though, even like the principal cube root of minus 8 plus 0i, it's not like they're throwing radicals around either. So they kind of don't even use radicals. And so it just gets really confusing. Radicals can be the radical symbol can be confusing. In particular, once you haven't taken a more advanced course in complex numbers. So with that, we just, anytime we're dealing with a radical symbol, except for this case here, we're just wanting to be thinking about all real numbers. We're inputting some pure real number from the all real number line perspective, where even in that case, we're not thinking about the number 4 as 4 plus 0i. We're just thinking about all real numbers, right? That's the inputs into the radical symbol, and the outputs are another real number, or maybe no solution. And the outputs are going to be some real number, except for this one special case where you have a square root of a negative number, then you have an imaginary number. But in general, the outputs are going to be some real number on the real number line, or maybe no solution. The no solution would be an even root other than 2 of a negative number. But it's still just going to be a real number that you're inputting into it off the real number line. That's the perspective that you want to take every time you're dealing with a radical. But when you're going through the complex analysis playlist, it's not posted yet, we'll expand on this, though, and try and clear up more confusion on radical symbols and principal roots, etc. Okay, so in the next video, we'll get started and go through this section.